Hey, welcome to Let's Get to the Marks. You can see I'm going through the GCSE Combined Science Trilogy higher tier paper. This is the May 2019 Physics Paper 1. There's 6 questions, hour and 15 minutes. Now, this is for combined scientists, but I would also strongly recommend this for people doing the separate Physics GCSE. Remember, everything in a combined science higher paper will appear in your separate triple GCSE as well. It's just if you're a combined scientist doing the triple GCSE papers, while useful, 20% of that roughly, is not going to come up. Anyway, what I suggest you do is you press pause at the start of each question, grab a pen, grab some paper, get your calculator, it's physics, and have a go at the question, and then unpause and I'll do the explanation. Let's go. All right, question 1. A student investigated how the current in a resistor varies with potential difference across the resistor. Figure 1 shows part of the circuit used. We've got this thing here with a plus. We've got this here. We've got this, and we've got this. Let's go down. 1.1, the student connected an ammeter and a voltmeter into the circuit. What is the correct way to connect the ammeter and voltmeter into this circuit? It's worth 1 mark. You could choose the ammeter, put it in parallel with the resistor, in parallel with the cell, series with the resistor, series with the resistor. The voltmeter, you've got some choices. How would you connect a voltmeter in here? And you've got those choices there. So why don't you have a go at the question? All right, I'm going to go through the answers. So the way we do this, and you have to know this off by heart, and if you get this, is a dead easy question. So if you carefully, it says the student connected an ammeter and a voltmeter into, what is the correct? Well, okay, there's no clue there, but the voltmeter is always connected in parallel to the component you are using. So the voltmeter is connected in parallel around the resistor. Often the reason why I try to reread this, often they will say they have here, look, they want to see how the potential difference, which is measured with a voltmeter, across the resistor. They will always use that language. So that's how you know, if you know that symbol is a resistor, so this is a resistor, the fact that they say across the resistor, that reminds you that the voltmeter must go across it. All right. Now, they want to measure the current in a resistor. This means our voltmeter can be placed here, and we call that in series, which means one after another. That's what series means. I could have put my ammeter there. I could have put it there. I could have put it there. Anywhere in series, it doesn't matter. You might say, well, what's this? This is known as a variable resistor, and that is for controlling the current, but we'll come to that later. So which of these answers goes with this? The ammeter must be in series with the resistor, so we can get rid of that and that. And the voltmeter is in parallel with the resistor, not in parallel with the cell. You wouldn't put the voltmeter around here unless you're checking to see if your battery, the voltage on the packet is correct. Okay, you wouldn't do that. Okay, let's go. Let's move on. Okay, we're on to 1.2. The student increased the resistance of the variable resistor. How did increasing the resistance affect the current? 1 mark. Okay, why don't you press pause? Have a go. It's really a 50-50. It's either going to increase the current or decrease the current. So what they're saying here, this is the variable resistor. When you turn that resistance up, resistance, think of current as like a river. If you're putting stones or putting something that resists, pushes back against the river, it's going to make it harder for current to flow. So high resistance means lower current, and they're always in that inversely proportional relationship. So what we want to say here is it decreases the current. Okay, so high resistance will decrease the current. Now, your volume control on your phone. So if you're turning up the volume on your phone, you've got your headphones on. What you're really doing when you turn up the volume on your phone is you're turning down a variable resistor and therefore allowing more current. So any sort of volume control is a resistor. Your dimmer switch in your bedroom, if you've got one of those lights where you can dim the lights, what you're doing there is you're increasing the resistance and that reduces the current, hence you get less light. You get the idea. The brightness on your phone is a variable resistor, the brightness button, all of that kind of stuff. Okay, so when you increase resistance, when you increase resistance, you decrease current. Yeah, right. 1.3, how should the student change the circuit to give negative values for current and potential difference? So let's go back up here. You can pause the video, have a go at that. How would we change this diagram to get minus values? So what we're saying here is your voltmeter, let's imagine the voltmeter is reading minus, sorry, oh my days, what am I do? The voltmeter is reading, let's say it's reading 2 volts, right? And let's say the ammeter is reading 3 amps. How can I make this negative? So it's minus 3 amps and minus 2 volts. And that's what the question's asking. So if you know, you know. What you've got to do is change the direction the current flows. Right now, the current is going this way. And if I want to change the direction, I need to turn this around. This is your cell or battery. It's actually a cell because it's a single unit. If there's 2 of those together, then it's a battery. But yeah, reverse the cell, essentially. Reverse the battery, reverse the cell. I don't know whether they'll give us a mark for battery, but reverse the cell will reverse the direction. Okay, I could say reverse the connections on the cell, i.e. the wires, so they're the other way around. It's totally, we can word that in different ways, but that's semantics, just changing the language to get the same answer. All right, name the type of relationship between current and potential difference for a resistor at a constant temperature. Okay, guys, there are three IV graphs, current and potential difference. So we call these IV graphs. And I'm going to show you, oh my days. So current has the symbol I and potential difference has the symbol V. And there are three of these graphs. You need to know these off by heart. Why don't you pause the video, have a go at this? I'm going through the explanation. So here we go. All right, so this is I and this is V. These are the positive values when the current is flowing one way around a circuit. And these are the negative values when the current is flowing the opposite way around a circuit. Now, you need to know three different components. One of these components is a lamp, a filament lamp. And a filament lamp goes up, 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 and then it goes off due to something called the heating effect. If we reverse the cell, we'll get a negative version of the same graph like that. So that's the filament lamp. Then we need to know the resistance also through something called a diode, which they might have later on in this paper. So here we go. There's a diode symbol, not very good, but essentially the diode will only let current go in one direction. So you get this kind of thing going on. And you don't get anything in the negative value because if you turn the battery around, the current won't be able to flow. It's only allowed to go in one half of the circuit, i.e. the positive direction. Okay, and then the third one you've got to know is for an ohmic conductor or just a resistor that is at a constant temperature. And the relationship we have here, oh my days, that is the worst line ever. Well, basically what I'm trying to show you here is for an ohmic conductor, its relationship is like that. If you keep increasing the current or the potential difference, the other one will go up. They are, how do we describe that straight line relationship going up like that? And hopefully you know that it means directly proportional. So it's directly proportional. Meaning, if I double the current, you double the resistance. If I triple the current, you triple the resistance. There's a directly proportional relationship between them. And you have to know that, this graph here, and that's what gives you that information for this. Write the equation that links current, potential difference, and resistance. You'll find this on your equation sheet. So I like to think of this one as you've got I for current, you've got V for potential difference, and R. The way I remember this is very itchy rash. So and I always remember things in terms of a triangle. And any way that you express this, as long as it's correct according to this triangle, which I do very itchy rash, and V over IR. This just helps me because I'm rubbish at math. So if I want to know current, I just do voltage divided by resistance. That's a divide line. That's a multiply line. If I want to do, if I want to work out the resistance, I do voltage divided by current. And if I want to work out the voltage, I do current times resistance. Now, how can I express this? I can express this like this, but you could write this in any legitimate way according to that triangle. So I could have put resistance equals voltage divided by current. It would, they're all the same application of it there. Okay, they're going to get us to apply it down here in this question. Let's move down to the next bit. Boom. That wasn't a very good boom. I should have gone boom. Right, 1.6. The current in the resistor was 0.12 amps. When the potential difference across the resistor was 3 volts, calculate the resistance of the resistor. So what we've been given here, just to remind ourselves, by now we've worked this equation out. Remember, you are being given the equation sheet, and that is a definite cert till 2027, the exam board have said at the moment. So you will 100% have that equation sheet if you're studying this at the moment. The current in the resistor was 0.12 amps. When the potential difference across the resistor was 3 volts, calculate the resistance. It's a 3 fat boom marks. So all you need to do to get those 3 marks, I mean, is put the correct answer will get you the 3 marks. But just in case you don't put the correct answer and you make some sort of error, just substitute these letters for the numbers. So you know that's I, current is I. You know, well, it even tells you the V there. So 3 volts equals 0.12 times R. And that is your first mark just for substituting the numbers in. Now you need to rearrange. We want to get R. So I want to divide both sides by I. What you do to one side, you've got to do to the other. So I'm going to do V divided by I equals R. Now, you're going to get a mark for the correct rearrangement. Now, you could show that with the numbers. So we're going to go 3 over 0.12, and that equals R. And what does 3 divided by 0.12 equal? I believe it is 25, but I need to bust out the calculator just to check that one out. So 3 divided by 0.12 is 25 ohms. Now, you will either get the mark for doing the symbols rearranged correctly or putting the numbers in correctly. It doesn't really matter which. And then you'll get one for the correct answer. And that's three lovely marks. Oh, I need to clear this. There we go. Let's get on to question two. If you're liking the video, make sure you hit the like. It massively helps out the algorithm, helps my video get to people, and encourages me to do more of these. Isn't that wunderbar? Dum, 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 dum. Okay, two. A scientist called the air inside a container. So they've got a container. Here it is. And they're cooling it down. So they're zapping it with cold. How do we show cold? Okay. The temperature of the air changed from 20 to 0. So it went down by 20 degrees. The volume of the container of air stayed the same. So what that's telling us is the amount of particles in there stayed the same. Explain how the motion of the air molecules caused the pressure in the container to change as the temperature decreased. So we've got an explain. We need to use science here. How the motion of the air caused the pressure to change. So you're going to get 1 mark for saying whether when it gets colder, will the pressure go up or down? There's 1 mark for that, which is a description, and then 2 marks for explaining how that works. So there is an equation that can kind of help you with this. I'm not sure it's 100% on your specification, actually, but it's kind of useful to know. Pressure is equal to force over area. And you definitely did this in key stage 3. So pressure is equal to force over area. And what we're talking about, the pressure in a container is caused by the force of particles colliding with the walls, which is the area of the container. So as you decrease the temperature, what changes about these particles and what changes about the collisions? So why don't you pause the video, have a go? I'm going through the answers. Let's go. So I'm going to say pressure, first of all, goes down. So the pressure is going to get less. Why is that? Because the particles have less kinetic energy. If you decrease the temperature, temperature is a measurement of the average or mean kinetic energy of the particles. Or I can say the particles slow down or the particles move more slowly, or are not as fast. Anything that's all semantics, all language, anything that says they're moving more slowly. So what I would say is this scores you 2 marks. There we go. Potentially. Let's put another 2 things down. Always to get 3 marks, I want to put 4 things down. So this means less collisions with the walls of the container, because it's the collisions that create the force, right? So then I'm going to say, which means less force over the area. Now you might say, why am I saying less force over the area? I'm talking, the area of the walls hasn't changed, but we've had less force. F over A. F has gone down, so P has gone down. All right, let's tick that up. So what I would say is all of these are kind of point scoring marks, okay? And you need 3 of those. Let's go. 2.2, the air contained water that froze at 0. The change in internal energy of the water as it froze was 0.70 kilojoules. The specific latent heat of fusion of water is 330 kilojoule per kilogram. Calculate the mass of ice produced. Use the physics equation sheet. Right, this is a really easy equation. And as I said, you're going to get the equation sheet. And essentially it is energy is equal to mass times L. And that's where L is the specific latent heat of fusion. So we've been given L, it's over here, and we're told that there. Look, specific latent heat of fusion. It's actually specific latent heat of vaporization at times, or heat of fusion. It doesn't really matter. It's just called specific latent heat. But yeah, in this context of going from liquid to solid, it's known as the specific latent heat of fusion. So that is L. Now we need to find the mass. So you just need to rearrange this. If I want to find M, I'm going to divide both sides by L to get rid of the L and leave M on its own. So I'm going to get E over L equals M. So all you need to do now is substitute the numbers. The internal energy, look, it tells you this is energy. So that is E. So we just need to do 0.70 kJ. We need to check the units. The energy's in kJ. The latent heat is in kJ. I don't need to change to joules or anything like that. And I'm going to divide that by the mass, oh, sorry, by the specific latent heat, which is 330. And that should give me the mass of the ice. Let's put that in. 330. So 0.7 divided by 330. What is that? 0.7 divided by 330. It is 0.002121. So the answer I get is 0.002121. What am I going to write this as? Well, I'm going to go like that. 0.00212. And there we go. It's going to get me three. All of the marks, all of the marks, all of the marks. 1, 2, 3. Beautiful. Okay, let's move on. Woo. 2.3, the air also contained oxygen, nitrogen, and carbon dioxide. So we've got, and we don't need the symbols for them, but just to remind you, O2, oh my days, nearly wrote, well, I did write N2, these are diatomic molecules, and then we've got CO2, bit of chemistry, lovely. Oxygen boils at -183 and freezes at 218. Nitrogen boils at -95 and freezes at minus 210. Carbon dioxide sublimates at -78. The scientists continued to cool the air temperature till it reached -190. So they basically made it so cold that it's -190. What is the state of each substance? Oh my gosh, I can't speak. What is the state of my brain? What is the state of each substance at -190 degrees? Put a tick in each row of the table. Oh my face. So essentially, you've got to say, is oxygen solid at -190? Is nitrogen solid? Is carbon dioxide solid? Or are they liquid or are they gas? Just 3 ticks, 1 in each row. Off you go. Pause the video. Okay, I'm going to go through the explanation. So look, essentially what you're told here, oxygen boils at -183. So oxygen becomes a gas at -183. So if we go to and it freezes solid, becomes a solid at -218. So it's a gas at -183 and it's solid because it freezes at -218. So what we have to say to ourselves is, when it's -190, what's it going to be? Well, it's not yet a gas. And I think what really screws people up, imagine there's 0. This is what really screws people up. There's -50. There's -100, right? Let's go down to our numbers here, like -183. And let's put -190. So which temperature is lower, -190 or -183? Well, obviously, there's +100 degrees. Obviously, -183 is warmer than -190, but that can screw with people's brains and they can think -190 is higher than -180. It's not. It's further from 0, so it's colder. So what they're saying is oxygen doesn't become a gas until here, -183. We're at -190, so it's not actually a gas yet, but oxygen is solid at -218. So it actually melts at -218 as well. So oxygen is in between that and that. It's going to be a liquid. Gosh, I made that difficult to understand. Nitrogen boils at -195. So nitrogen is boiling, turning into a gas there, and freezes at -210. It becomes solid at -210. We're at -190, so it can't be a solid because it doesn't become a solid till -210. And it boils at -195. So guess what? It boils here. What does that tell you? It tells you that nitrogen is a gas at any of these temperatures above that. So nitrogen is a gas. It's already boiled at -195. You've just made it warmer to -190. It's still going to become a gas. If you make a gas warmer, it stays as a gas. Okay, carbon dioxide sublimates at -78. Do you know what sublimates means? Sublimates is when you go from a solid and you have no liquid phase. You skip the liquid and you go straight to the gas phase. Over here is liquid. Well, they kind of move around each other, are in contact with each other. They should really be touching, but yeah, so there's solid, there's liquid, there's gas. Sublimate means you go from solid to gas. So that doesn't happen till minus 78. Are we at minus 78? No, we're nowhere. There's minus 78. We're at minus 190. We're nowhere near minus 78. So it's still going to be solid carbon dioxide. It doesn't have a liquid phase. It doesn't turn to a gas till minus 78. We're not that warm. We're down at a super chilly minus 190. Anyway, that was a really hard conceptually question. Those are always difficult to get your head around. So don't slap yourself in the head if you got it wrong. Okay. They're always difficult, those states ones and temperatures. Right, what we got here, 2.4. The air also contained a small amount of argon. As the temperature of the air decreased from 20 degrees to minus 190, the argon changed from a gas to a liquid to a solid. Explain the changes in the arrangement and movement of the particles of argon as the temperature of the air decreased. 6 marks. So this is a really nice 6 marker. Grab a pen, grab a scrap bit of paper. What I want you to do is pause the video and have a go, and then I'm going to go through the explanation. What I would say is the way to break this down, explain the changes in the arrangement. That means how are the particles arranged? What's the pattern of the particles in each? And you must talk about the movement of the particles as the temperature gets colder. So as it gets colder, are we going from solid to gas as you get colder, or gas to solid? Well, as you get colder, you're going towards freezing and becoming a solid. So we want to start off, and going through the explanation here, guys, we want to start off as a gas, and then we need to explain this. And as long as you know your diagrams, you're going to be all right. You need to explain that, and then the change to that. Okay. So what is the change? And remember, we need to talk about each of these states, but each time we need to mention the movement and the arrangement. So let's go. So it starts off as a gas. So as a gas, the particles are far apart. The only problem is particles does not have a K in it. Right, there we go. Right, as a gas, the particles are farther apart. What have I talked about? That's the arrangement. Now, how are they moving? So they are moving randomly and quickly. Okay, they've got lots of kinetic energy. I'm not going to talk about the energy because it didn't ask me to. So I'm just going to talk about the particles are far apart. They're moving randomly and quickly. If I want, I could say they have lots of kinetic energy. We could throw it in there. And they haven't asked me to talk about forces either. They've not mentioned forces. But if I want, I could say there, I'm going to do it just, but these are not necessarily what I would include. There are negligible. Let's just say there are no, because it's easier, isn't it, than trying to spell negligible. There are no forces between particles. There you go. So I've mentioned forces as well. I don't think the forces thing is what they're after because they didn't mention it there. But you know what? They're just going to say ignore because it's totally correct what I've said. Right. Then as it cools, it loses kinetic energy. Now, did I need to say that? Maybe not, but it just flows nicely, doesn't it? It's losing kinetic energy. The particles, what can we say about the arrangement? Become closer together. So there's smaller space between the particles. Semantics, that's you're going to get the same answer for saying the same thing. Okay, so whether you say the particles are closer together or the gap between the particles is smaller, that means the same thing. So the particles become closer together. They still move randomly. So it's still random movements. They still move randomly, but this time around each other. They're in contact actually with each other. We often don't show that on our diagrams. It's one of the limitations there. The particles, you can't compress a liquid because the particles don't have really spaces between them. Now, I know I said I shouldn't talk about it. The forces between the particles, there's no need to talk about this, but are weak. And it's just me putting it all down there because you might be revising and you might get a question like this, but it might also say talk about the forces and you've memorized the answer to this and you're like, but I didn't get all the marks. Why? And it's because if it asks you to talk about the forces between the particles, then you've got no forces in a gas, weak forces between the particles in a liquid, and then you can guess what happens in a solid. Oh, and I didn't say the particles are moving more slowly because it says movement. I talked about the random nature, but I should say, let's not forget that particles are moving more slowly than comparative in a gas. Okay, so more slowly compared to what? Well, a gas. And then in the final stage, we want to say, then it becomes a solid as the temperature drops um, to freezing point. So as the temperature drops to freezing point, it becomes a solid. Particles are touching, no gaps. I'm just going to say I'm running out of room, so I'm going to. Okay, no gaps, strong forces, um, and vibrating. Oh my gosh, vibrating. No, I mean vibrating. Vibrating around fixed positions. They love that, eh? Right, you're basically saying they're not moving, they're just vibrating. There's no gaps. The movements aren't random. I don't need to put the movements aren't random because, or that they've slowed down because that's obvious. They're no longer moving, they're vibrating. A vibration is moving from side to side, backwards and forwards around the same point. So, they should accept all of that. I've really just have I described the arrangement? Yes, they're touching each other. I might want to say they're in a regular. Let's just add the word regular in. For example, particles are touching, no gap, strong forces vibrating around fixed positions in a regular arrangement, or I could say in layers. Okay, I'm just trying to cover. Sometimes the mark scheme gets funky, doesn't it? And says, "Oh, you didn't mention this." And there's kind of like two for each. Now, one thing I might improve this by set is saying um, it's called, the temperature is cooled until it reaches the melting point and then it becomes a liquid. So I might want to add, once it becomes a melting point, then it becomes a liquid. Once it hits the freezing point, which I've put there, or boiling point, sorry, freezing point, or sorry, oh my good gosh. Once we reach the boiling point, which is like the same as saying condensing point, then it becomes a liquid. Once it reaches the boiling point or freezing point, then it becomes a solid. Anywho, I don't think you need that. That's 6 marks. Where'd it go, huh? Okay, let's move on. Okay, so question three. A hybrid car has an electric motor and a petrol engine. Petrol is a non-renewable energy resource. What is meant by non-renewable energy resource? Why don't you pause the video, grab your pen and paper, have a go at writing these down. Make your revision active. Even if you don't have a pen and paper and you just try and quiz yourself, bullet point, use your fingers as the bullet points, zing through and see how many marks you get. All right, I'm going to go through the answer. So a non-renewable energy resource means it's going to run out one day. Yeah, you could use the words finite if you like. That also means going to run out. So let's just put it is going to run out in the future. So we could say it is finite if you like that. Um, yeah. Example would be any of the fossil fuels, petrol, of course, made from the mixture that is crude oil or is separated from crude oil, but you've got coal, you've got gas as well. They're also finite resources. Okay, 3.2. The electric motor in the car is powered by a battery. To charge the battery, the car is plugged into the mains supply. Now, the mains in the UK is roughly 230 volts, give or take a bit. There's a little range as it's not constant. The power used to charge the battery is 6.9 kilowatts. Calculate the current to charge the battery. Four fat marks. Now, up till 2027, you're going to get the physics equation sheet, so don't worry about that, folks. And this is the equation. We've got the voltage, we've got the power. That's what kilowatts is. It's a power. And we need to find the current I. And so what you do, once you've identified all the symbols in the question like that, then go to your equation sheet and say, is there an equation that can give me this? And there is. It's called PIV. P equals I times V. I love a triangle. Um, yeah, they get me excited. So P over IV because they help me rearrange. So I need to find I. So what you do with the triangle is you cover up the I and you go P. This is the divide line. P divided by V equals I. So if I do that, P divided by V equals I, I've selected the correct equation and I've rearranged it. I'm gonna get some marks here, possibly one, possibly two. Now all I need to do is substitute the numbers in. Now you've got 6.9 as the power and you've got the volts as 230. Now if you do this, you're going to at least get 1 mark. The Problem is, you're going to get another mark, so like 2 out of 4. Problem is, kilowatts, the K means 1,000 watts. So I need to convert that into watts, and power is measured in watts, not kilowatts. So I'm going to do 6.9 thousands over 230. Now I've done that conversion. That is going to get me an extra mark. So, and then we're going to bus out the answer. So you're probably going to get, you would get, maybe you'd even get three if you don't do the conversion. I mean, you get the wrong answer, so it's not the greatest, but let's go and smash that in the calculator. So 6,900 divided by 230, we're going to have 30 amps as our current. And there we go. So I'm guessing you're getting one for selecting the correct equation, you're getting one for rearranging it, you're getting one for converting the 6,900, the 6.9 kilowatts to 6,900 watts, and then you're getting one for the correct answer. Awesome. 3.3. Mains electricity is an AC supply. Explain the difference between direct and alternating potential difference. AC stands for alternating current, but what is the difference between direct and alternating potential difference? So really, it's the direct direct potential difference goes in one way around the circuit, goes in one direction, um, only positive or negative, whereas um, alternating potential difference, um, oh my days, oh my days, causes a current to flow in both directions around a circuit, both plus and the negative direction. So essentially, if you have just a direct voltage, you will only get a current going in one way around a circuit. If you have an alternating potential difference, your current will flow in both directions around a circuit. It will go from positive to negative and then negative to positive. So both directions around the circuit. And that's why it's called alternating. Okay. 3.4. The cable used to connect the car to the mains electricity supply has a low resistance. Yeah, it's going to be a big, fat cable. So if you've got your car like this and you're giving it a charge, you could charge it with a skinny wire like that, or you could get a big fat wire. And there is better to, when you're trying to use a lot of power, it is better to have fat cables, like the ones that plug your oven in or your washing machine. They're going to be fatter than the ones that plug your laptop in. So the ones that plug your car in, you're going to have a fatter cable. Explain why it's better to use a cable with a low resistance than to use a cable with a high resistance. Right. A low resistance, do you remember we have V equals I over R. So if I have a low resistance, remember the potential difference in the UK is 230. So let's say I want to charge my car quickly. I want a big current. Well, if I use a low resistance, I can get a bigger current while having the same voltage. I'm not allowed to change the voltage in the UK. It's 230 from the main supply. So you can see that, let's say the resistance was 10. I had 10 ohms and I have, oh my good gosh, what would we say, 23 amps. Okay, I'm going to charge the current. So 230 divided by 10, I've got 23 amps, 10 resistance. Let's say I lower the resistance to 1 ohm. What is the current going to be? Well, the current is going to be 230 amps. So for the same voltage, I'm going to get a bigger current and I'm going to charge my car more quickly. So what we're going to say is low resistance means we get a higher current for the same voltage, which in the UK is 230. You can't alternate, you can't change that. So I don't know if we need to put this, but the car will charge more quickly because current, of course, is your flow of electrons or whatever it is per second. Yeah, well, it's how much charge per second, isn't it? That's what current is. So yeah, you're going to charge it more quickly. Okay, cool. I think I've covered everything there. Low resistance means we get a higher current for the same voltage. I think those are the two main points. Let's move to question four. Okay, more electricity. That's lovely. Figure two shows a circuit that a student built. So we've got two cells, that's a battery, we've got a filament lamp, and then we've got two resistors. 4.1, the lamp has a resistance of 10 ohms. Thank you for that. Let's graffiti on this as we go. It's the best way, and you should learn to do this technique in exams. So the lamp has a resistance of 10. Each resistor has 10. So let me write 10 on each of these. You see, we're actually graffitiing and annotating as we go. What is the total resistance of the circuit? So is it 20 to 30? Is it exactly 20? Is it exactly 30? Is it less than 20? So you'd look at that and, okay, a common mistake will be to go, oh, it's 30, right? 10 plus 10 plus 10. But here's where our circuit rules come in, and you have to memorize these off by heart. And there are some circuit rules. So in series, when things are in series, resistance adds up. Now that's a stupid statement, but essentially what I mean is if you put two things in series, this is in series with this, so you go 10 plus 10 is 20, whatever. In series, the resistance adds up. When things are next to each other, you add them up. However, when they're in parallel, this is the situation. When resistors are in parallel, this is a weird rule. I could explain it if I went into more detail, but I'm not going to. When resistors are in parallel, the total resistance is lower, okay, than the smallest individual resistor. And you can do this by if you express the equation as total resistance 1 over T, or 1 over T is equal to 1 over R plus 1 over, yeah, 1 over R, well, whatever, R1, R2, depending on how many resistance you've got. Okay, but we don't need to get into that business. So what we're going to do here, we're going to say, right, that's 10 ohms. So I'm looking to add it to these bad boys. Now, is the total, if we use this rule here, is the total resistance going to be 20 ohms? No, I said the total resistance has to be lower than the smallest individual resistor. So when you add these together in parallel, remember this is parallel, they must be lower than 10. So the maximum they can be is 9.999. That's the maximum they can be. So actually, when you add these together, if you go that plus that, you get 9.9. Now, these two are in series. The parallel resistors and that are next to each other. So we just add them together. So we are really going to get like 10 plus 9.9. Now, it might be lower than 9.9. It might be 8. It might be 5. It can be anything that's lower. You can actually calculate it by doing 1 over 10 plus 1 over 10 equals 1 over the total. But we're not going to do that. So 10 plus 9.9. So it's going to be less than 20, the total resistance. We know that for a fact because it's 10 plus something less than 10. So there we go. And that is one of the more difficult circuit rules in circuits. Explain your answer to question 4.1. So now we just need to put our answer in, and our answer is going to be resistors in parallel. The total resistance is lower than the smallest individual resistor. Um, ah, so the total resistance of parallel resistors is less than 10 ohms. This is then added to the resistor in series, which is 10 ohms. I think I've explained that. So it must be less than 20. Anywho, I think the main bit there is just that the resistors in parallel, total resistance is smaller than the individual resistors, and that will get you the marks. So they're just checking you knew the rule and you didn't guess it, which is pretty mean. The student replaced one of the resistors with a thermistor. Draw the circuit symbol for a thermistor in the box below. So you've got these two sensing ones. You have a thermistor and an LDR, a light dependent resistor. Now, the light dependent resistor you sometimes get asked about, and the light dependent resistor depends on light. Depends on light. So we draw like we draw kind of arrows going down there, and I should have really drawn the circle around there, but that's not what we're being asked to do. We're asked to do the thermistor. So you start off with a resistor, the ISTOR. This bit tells you it's a resistor. So draw the shape of the resistor. Same with a light dependent resistor, any resistor, variable resistor. You draw this rectangle, and then all we need to do is put a tick through it, a backwards tick like that, and you kind of get a T for temperature. She's got us forming there. Anywho, there we go. I could put a circle around that if I want. Let's put a circle around it. Way. Yeah, I don't really like that. Anyway, that's the marks. Let's move on. 4.4. The student increased the temperature of the thermistor. Explain how the current in the thermistor changed. So what we want to do here, hold on. Do we have a circuit diagram of this? We don't, do we? No, we don't have. Oh yeah, no. Explain how the current in the thermistor changed. Okay, well, so thermistors have, here's our thermistor. Thermistors have a little graph you have to know off by hot, and you have resistance there and you have temperature there. And essentially, as the temperature increases, the resistance goes down. So the student increased the temperature of the thermistor. Explain how the current changed. So think about it. As the temperature gets hotter, what happens to the resistor? You have to know this graph off by heart for a thermistor. It's identical for a light dependent resistor. So learn it, put it on a revision card. So what we want to say is resistance goes down as temperature goes up. So the current in the thermistor increases. There we go. Current must increase because the resistance goes down. So what we want to do here, 4.5, figure 3 shows another circuit the student built. You can see we've got two batteries, we've got a filament lamp, we've got a resistor, and we have a switch in parallel to the resistor. Explain how the potential difference across the resistor, which is this, and the lamp will change when the switch is closed. Again, this is testing us a little bit on our circuit rules. So what we need to know here is if this closes, originally the current had to flow through this resistor and through the lamp, right? Current is the flow of the electrons. So that is going through the in over time. So that is going through there and through there. It's being divided like that. When we close the switch, this is what's going to happen, which is a little bit different. When you close that switch, by the way, why don't you pause the video, have a go at answering this, and then you can watch my explanation. When you close the switch, it doesn't have to go through the resistor. It's a short circuit. The switch has no resistance or the same resistance as the wire. So essentially, virtually has no resistance relative to the resistor. So now it can go this way through the light bulb. So what I would say is you're going to end up with no current and therefore no potential difference here. So in the resistor, the voltage, which is potential difference, in the resistor is going to decrease because the switch has no resistance, and so therefore current flows through the switch instead. And let's put that. So let's go. The resistor, the voltage will become zero as there is short circuit, you can say, or the switch has zero resistance, so the current flows through the switch. So the current is going to go through the path of least resistance, where it gets least opposition. And now all of a sudden you've created this pathway, which has got pushback, pushing the current back. And you've created an easier pathway. The current's going to flow that way and then through the bulb, okay? Because that has zero resistance. Cool. We've explained that, so we're going to get 2 marks. Now, what happens to the voltage in the lamp? And let me explain this one for you. You could always, obviously, you should have a go at this first, and it's 2 marks. So you need to say, if will it go up or down is going to be 1 mark, and then explain that. So if you just said the voltage goes down, the voltage goes up, you'll get 2 marks because the voltage is going to increase. So the voltage will increase in the lamp. Now, if you know your rules of circuits, you'll know why. In a series circuit, and essentially this is now a series circuit, the voltage gets shared between the components. Obviously, the voltage adds up to the total. And what we're going to do here, unlike the current, which is the same everywhere, the voltage adds up to the total. And so what we have a situation is, let's say this was 6 volt battery, okay, then we would have had 3 volts there and 3 volts there. That's the way a series circuit works. You've just taken that out of the equation. So that lamp is going to get all 6 volts. It now gets all of the volts from the battery. And that's the way series circuits work. The voltage of the battery is shared out between the components. So the voltage will increase in the lamp, we could say, because the resistor, ah, the resistor no longer has voltage. So um, the lamp gets all of the battery's voltage, or we can say the voltage is the same as the battery. Okay, so that's one way to explain it. That's the way I'm going with, folks. You could also say because current in the lamp increases, why does the current increase? Again, if there was 8 amps here, the amps, remember, will be divided as well in a series. So well, the amps will be the same everywhere, but obviously the more components you add, the higher the resistance, the amps goes down. So you could say there is another way to explain this is there is lower overall resistance in the circuit, therefore the voltage in the lamp, the current in the lamp increases, and therefore the voltage increases. Okay. Okay, question 5. A student investigated how the mass of water in an electric kettle affected the time taken for the water to reach boiling point. The kettle switched off when the water reached boiling point. Figure 4 shows the kettle. Here's figure 4. Here's your kettle. And there's a heating element here. The heating element of the kettle was connected to the mains supply. Explain why the temperature of the heating element increased. So what have we got going on here? Why don't you pause the video, have a go? I'm going to go through the 2 points. So why did the heating element go up in temperature? What kind of energy did it gain and in what store and where from? So this is really chemical energy from the power station being converted into electrical energy as the system or the method of transfer, and then going into heating energy in the metal element. So we want to say thermal energy in the thermal energy stores. Don't forget the word stores. Um, energy in the thermal energy stores of the metal element increase as electricity or electrical or as energy is transferred to them via electricity, as energy is transferred to them via electricity. Now, we weren't given specifics, so we might think, oh, do we have to mention the chemical energy in the power station from the coal or the gas that was boiled? We haven't been actually told what is the energy store or what energy resource is being used. So we just know that electricity is being transferred down the cable, and we have the kinetic energy or the thermal energy store is increasing. I guess the kinetic energy store might increase as well. That normally goes hand in hand. Okay, right. Let's zing on. We might also get some sound energy when the kettle goes on. I don't know. What noise does a kettle make? 5.2, give one variable the student should have controlled. So they're changing. Let's look at what the independent variable is. It looks like they're seeing how they're measuring the time. So that's dependent variable. They're changing the mass of water affects it. So what should we do? The starting temperature of the water should be controlled, right? Because if they're starting at a higher temperature, so I'm going to go with the starting temperature of the water. The starting temperature of the water. They're changing the mass of water, so you can't say control the mass. So the starting temperature of the water, we need to allow it to cool each time and go back to the original starting temp. Figure 5 shows how the mass of water in the kettle affected the time taken for the kettle to switch off. So time taken for the kettle to switch off, as the mass in the water increases, so does the time taken for the kettle to switch off, but it's not a straight line. So just why the line on the figure does not go through the origin. Okay, so we've said it takes time for the kettle to switch off. It does not do so instantly, as the heating element takes some time before it increases in temperature. So essentially, that electricity has to change into energy in the thermal store, and that's going to take a few seconds. So it looks like it takes about 10 or 15 seconds before that can happen. Now, the next question, folks, says he Sue, suggests why the results. I've lost my position. Suggest why the results are given non-linear pattern. So as the mass increases, the time taken for the kettles to switch off, it takes a bit longer. It's not as rapid at switching off. So it's taking longer and longer for the time to switch off. And I guess as the mass of the water increases, the efficiency of the kettle increases. So as the mass of water increases, less energy is lost to the surroundings. I guess it's to do with the surface area to volume ratio and things like that. Okay, I can't spell. Let's move on. Bish, bash. Oh gosh, ticking everything. Tick, tick, tick. Let's go. 5.5. We've got a calculation. The power of the kettle was 2.6. So what I like to do with calculations, guys, is I like to, it's a 6 fat marker. I like to identify what we're dealing with. That's power. 120 seconds. What do you think that is? That's time. 0 0.8 kilograms. That's mass. Then I've got delta T. That's temperature change. Sometimes written like this, if you really love it, the theta sign. Calculate the specific heat capacity of water using this information. Give your answer to two significant figures. So the specific heat capacity of water. Now, I like to write the equation like this. Q equals MC delta T. But maybe in AQA, you will be familiar with it like this. Change in energy, or maybe I should put the triangle first, equals mass times specific heat capacity times, and then they use this symbol. It means the same thing, the change in temperature. Okay. So all we need to do is substitute what we can in here, and let's have a go at that. And we need to rearrange. We are trying to find C. So if I want to find C, I need to divide the energy change by mass and by change in temp. So we're going to get like the change in energy over the top of the mass times the change in temperature. Gosh, I hate that symbol. Looks like a smiley face with no eyes. And that is going to give me the specific heat capacity. So I'm going to get a mark for doing that. Now, what I also need to think about is what are all these numbers? So the mass is 0.80 kg. Great. The temperature was 18 to 100. So I want to times that by 100 minus 18. Essentially, that is going to be 82. And then divide by the energy. All I need to do now is work out what the energy is. Now, notice they've not given us joules. So how are we going to find the energy? Well, we have been given the power and we have been given the time. And you, Ray, you might remember there is an equation, EPT. I'm inept or I'm apt. I'm capable of this. Okay, E, energy over power times time. You'll find that on your equation sheet. So we can work out the energy by doing the power times the time. Now check this. We've got to do a unit conversion there because K means thousand. So I need to do 2.6 times 1,000 to get my power in watts. And what we're going to find is we have 2,600 watts. That's my power. Now I need to times that by the time. The time is already in seconds. So if they give me 2 minutes, I'd have to times by 2 to get seconds, but already got that. So I'm going to do power times, that is seconds, but the symbol for that is a T. So P times T is going to give me the energy. So let's do that. 120 times, what was that? 2,000. Oh my days, 2,600 equals 312,000 joules. So 312,000 joules. Now that I'm dividing, folks, by the mass, 0.8 times 82 for the temp. And that is going to give me bish bash bosh. 0.8 times 82 equals that. I need to do 312, one bum bum, divided by that, diddly d, 4,756.09. 4,500, no, 4,700 856.09. Now look, they want two significant figures, two bad boy figures. Well, that means I can either write this as 4,700 or 4,800. I'm only allowed two numbers that aren't zeros. So two numbers that aren't zeros, I can either go 47, rest zero, or I can go 48. You can see it's got a 5, which is bigger than 4. So we're going to round up and we're going to put this as 4,800 joules per kilogram. Are we going to get all of the marks? All of the marks, all of the marks, all of the marks. On there. Jeez Louise, I don't know what was going on there. That's just insane. Right, I want to zing all the way, all the way, all the way down. Sorry if I swore, sorry if I swore. All the way down, all the way down, all the way down. Oh, here we go. Right, question 6. Lanthanum 140 is a radioactive isotope. A nucleus of lanthanum 140 emits gamma radiation. What happens to the mass number and the charge of the nucleus when the gamma radiation is emitted? Emitted means goes out. By the way, this number 140 is just the way of naming that isotope. You don't normally use that in a calculation. So what happens to the mass number and the charge of the nucleus when the gamma radiation is emitted? So you've got to wonder about what gamma radiation is. And you should know the symbol. It kind of looks like a weird Y, and it has 0 and 0. I probably did them on the roof. Has zero mass, zero charge. And so the nucleus, nothing happens. Stays the same, stays the same. Absolutely nothing happens to the mass number and the charge of the nucleus when gamma is emitted. Okay, because it's not a particle, it's a wave of electromagnetic, it's part of the electromagnetic spectrum. It's just some energy. It's a wave of electromagnetic radiation. Right, enough of my whiffle waffle. Why is it difficult to detect gamma radiation? Well, why is it difficult to detect? What does it say? Why is it difficult to detect gamma? Well, ooh. Well, it's got good enough penetration, but it's not very ionizing. So it has no electrical charge. So it doesn't have any charge. So it's not positive or negative. So it's very hard to read. It doesn't create a current like some of the others can be detected electrically because they cause a current to flow in the detector. So there we go. It's not positive or negative. 6.3 activity is the rate at which the radioactive source decays. A teacher measured the count rate from a sample of lanthanum 140 using a Geiger-Müller tube. Explain why the count rate was less than the activity of the sample of lanthanum 140. Okay, so what this is testing you on, and what you have to know, I'd make a revision card if you don't know it before your exam. Get it done now so you're ready for your GCSE. The activity and the count rate are two ways of measuring radiation, but they're different. Okay, so activity is the amount of radiation. So I'm going to give you the definitions. Activity is the amount of radiation released per second from an isotope that's decaying, whereas your count rate uh, I'm doing a lot of I tend to do that when I can't spell. I've got fat fingers and I hit more than one key. So the count rate is the amount of radioactive particles, same thing, but that hit the detector every second. So there's a difference. You might say, well, what's the difference? Both are every second, the amount of particles per second. Yes, both are the amount of particles per second. Let's imagine this green thing here is my radioactive material and it's giving out radiation. I don't know why it makes that noise. So it's giving out 5 every second. Let's say 1 second passes and it gives out these 5. Well, if I place my detector here, detector D. Don't ask me why it's shaped like that. So if I just place my detector there, how many of those are going to reach the detector every second? Only 1. So the count rate would be 1, but the real activity would be 5 per second. So 5 isotopes are breaking down every second, but only 1 is reaching my detector. Now you might say, doesn't this make count rate useless? No, it still means if I compare it to another material that's got double the count rate. So let's say this is material two and it's got 6, 7, 8, 9, 10. This is firing out 10 bits of radiation a second. Well, my detector is going to detect 2 a second. So it still tells me, oh, the radiation has doubled in this area. So it's very good. It just doesn't give you the actual amount of radiation that's released, but it is proportional to the amount of radiation that's released. Now, enough of that waffle. I've got to put this into 2 marks. Explain why count rate was less. So we want to say count rate is only the particles that reach the detector every second. It is not the activity, which is the total particles decayed a second. Oh my gosh. So I think I've made that pretty clear in that answer, and that is the 2 marks. So if you don't know the difference, get a little flashcard, revision card, one of them little revising cards, put on one side, what's the difference between count rate and activity, 2 marks, and then on the back, write 2 points, write what they are. And there you go, you'll get the marks for just saying the definitions. Super. Okay. The teacher investigated how the thickness of lead affected the amount of gamma radiation that could pass through it. So what they're doing here, got a Geiger Muller tube, they've got a sample, and this is going into the detector, and we're getting a click every time that gamma hits it. So figure 6 shows the apparatus, sample of lanthanum 140, which is decaying. We've got a sheet of lead, we've got the Geiger Muller tube, GM tube. You have to know that as well. You could be asked what apparatus do you use to detect radiation, GM tube. Okay, explain why the teacher stood as far away from the apparatus as possible. What is it about gamma? Gamma is only lightly ionizing, but it's quite penetrating. So we want to say gamma is highly penetrating, not ionizing. Oops, and has a high range. I'm sure I should say a large range. I don't know. It is also ionizing. Now, I know it's the least ionizing, but gamma radiation can still give you cancer. So it is also ionizing and could damage cells. I could say could damage cancer as well. The teacher's trying to avoid getting irradiated, I should say, not contaminated. Okay. Table 1 shows the results. We've got the thickness of the lead. Look what happens as the lead gets thicker, the count rate goes down. So the teacher concluded the count rate was not inversely proportional to the thickness of the lead. Explain why the teacher was correct. So actually, it's a correlation. It's not inverse. Now we need to explain. So we can say when the thickness was 1, the count rate was 60. So I'm going to say that as so when thickness was 1 centimeter, count rate was 60. If it was proportional, when the thickness was 2 centimeters, have a look, peoples. When the thickness was 2 centimeters, when we've doubled it, right? We've doubled the thickness. What should happen? The count rate, if it's inversely proportional, it should half. So what I didn't put here is I didn't say the word. So if it's inversely proportional, then when the thickness was 2, the count rate should then be 30. It is not, it is 18. So I've just proved that it is not directly proportional. And I've proved that it's not, I've proved that it's not inversely proportional. However, it is an inverse relationship. So there is an inverse relationship. As thickness increases, count rate decreases. So the inverse bit is correct. It's the proportion that's not correct. Okay, so wunderbar. Right, let's give ourselves all of them 3 bad boy marks. That was quite a hard question, so don't beat yourself up too badly if you didn't get it. Right, lanthanum 140 can emit beta radiation and change into cerium. Complete the equation showing the decay of lanthanum 140 into cerium. So what you've got to know with beta, sometimes beta they use this symbol and sometimes they use E. You can pause the video, have a go, try and get the 4 numbers down. Okay, beta has the symbol 0, 1, and obviously they're using an E here. It's just an electron. Electrons have virtually no mass, so we say that is 0. We say this is -1. I didn't write it on the line, I know, but 0 and -1. And all we've got to do is make sure that all the numbers on this side, mass is conserved and charge is conserved, so it's equal over there. So 140, 0 plus that must be 140 because then we've still got 140 up there. And then 57, we've got -1. This must be 58 because 58 -1 is 57. So either side of the arrow must balance, and that's going to get you 2 marks. Right, let's move on. We're near the end of this one. We have another graph. There are isotopes. There are other isotopes of cerium which are radioactive. Different isotopes of cerium have different half-lives. The half-life of an isotope can be found by studying how the number of atoms changes over time. Figure 7 shows how the number of atoms of cerium 148 in a 120-gram sample changes over time. So we can see the number of atoms is decreasing over the time. Let's go down. Determine the ratio of the number of cerium atoms in the sample when it was 100 seconds old compared with when the sample was 350 seconds old. Use the data. So we've got to use the graph. That's going to get us 2 marks for using the graph. And then we need to determine the ratio of the number of atoms in the sample. So it should be quite easy. We've got 100 and 350. So I'm going to do this up here on the graph. So what you're looking at here, guys, when it is let me go back down, see what they're saying. What are they saying to me, bruv? What they're saying, bruv? Determine the ratio of the number of cerium atoms in the sample when it was 100 seconds old compared when the sample was 350. Okay. Oh my gosh. So when it's 100 seconds old, we can find the number. And there you go. That's how many atoms are in there. So at 100 seconds old, number of atoms would be 1.3. So the number of atoms is 1.3 times 10. What does that say? To the 23. So I'm going to do that. So that's the number of atoms when it's 100 seconds old. How many atoms would be left when it is 350? Well, guess what? I'm going to have to know the half-life in order to do this. So this is quite tricky. I'm going to have to work out the half-life. So what I'm going to do, guys, is I'm going to say, well, it's 5 there. So when it's 2 at 0.5, what you do is you find the start. When you want to work out the half-life using a graph, find the start, so 5, then go to halfway, half, i.e. half-life. Now draw my little arrow down, line down. The half-life is, I think that would actually be there. The half-life is actually 50 seconds. So every 50 seconds, the number halves, right? Every 50 seconds, the number halves. So we start at 1.3. What will it be in 50 seconds? And we need to do that until we get, so we need to do that until we get to, whatchamacallit, 350 seconds. So this is going to be between 100 seconds. And so this is 50 seconds, 50 seconds later. So 350 minus 100. We're going to do this for 250. So I'm going to want to do 5 of these. Oh my days. This is disgusting. Oh gosh, I better check the mark scheme, make sure this is the way to do it because this sounds pretty disgusting. So 250 seconds later, how many atoms are going to be left? Well, guess what? Each time I do this, I've got to divide it by 2. So I need to divide by 2, 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 divide by 2. You get it. Divide by 2 to the 5. So let's do that. 1.3 times 10 to the 23. Let's divide that by 2. And if you do that, I'm going to write the numbers in because it's just going to be a pain in my butt and I'm going to do it even though it's a pain. So I'm going to get 6.5 times 10 to the 22 here. Now I'm going to divide by 2 again and we're going to get 3.25 times 10 to the 22. 3.25 times 10 to the 22. So that's there. Then we're dividing by 2 again. And I'm going to get over here, it's going to be like, this is so messy, 1.625 times 10 to the 22. Let's divide by 2 again. I'm going to get 8.125 times 10 to the 21. So 8.25 times 10 to the power of 21. And then for my final division, I'm going to divide by 2 again. And we're going to get 4.06 times 10 to the 21. So 4.06 times 10 to the 21. That was actually a really hard question. You had to calculate the half-life first and then work out how many decays it will have gone through, how many times it would have halved to find the final amount of atom at 350 seconds. So at 350 seconds, it's going to have 4.06 times 10 to the 21. At 100 seconds, it has 1.3 times 10 to the 23. So what we need to do is divide both by the smallest to get into the ratio. 1.3 times 10 to the power of 23. And I want to divide that by the smaller number, which is 4.06 times 10. Obviously, it's smaller because there's less left to the 21. Okay. And then I'm struggling here, peeps. Okay. Geez, that took so long. I could have grown a full beard by then. Right. Let's something to 1. So what do we want to do? 1.3 times 10 to the 23 divided by answer. Bish bash bosh. It's 32. OMG. Look at that big fat equation. Right, 32 to 1. That's the answer. Oh my God. I think that's one of the sickest combined science physics questions I've seen. That is disgusting. Ugh. Determine the activity of the sample of cerium when the sample was 20 seconds old. Okay, 6.8, last one. Determine the activity of the sample of cerium when the sample was 20 seconds old. We're going to have to do a tangent here, folks. That's absolutely foul and disgusting. I have to be honest with you. Right, we've got a curve. So we need, remember the count rate is the number of particles that decay a second. Did it want the count rate? Well, no, it must want the activity. Yeah, so it's the activity. So the number of particles that decay a second. So we want to draw, basically find the gradient of this line, and that is going to tell us how many particles decay every second. So we need to draw a tangent here. It's going to be a little bit hard to draw this tangent, actually. It's almost a dead straight line, isn't it? It's almost a straight line. So that there is almost straight. So let's get rid of these lines. And maybe like that. Yeah, I'd say maybe like that. I'm going to go all the way to there. Now, all you got to do is do your change in Y over X. So I'm using the whole thing as much as I can. So I'm going to go with that. And I think that's going to end around 90. So I'm going to go like this, 90. So I'm trying to make it as easy as I can for myself so I don't have to do a lot of adding up. And I think that's 4.8 times 10 to the 23. I'm sure that's like the worst tangent ever. I should have probably just done a little one like that, but I'm just using the whole thing on the axes. So you could just make a little triangle like that along this straight line, but I'm doing that. I think that's going to finish about 90. So it's when you're working out the tangent, you want to do change in Y divided by change in X. There's no V in change and there's no dot. So it's change in Y over change in X. And that's going to give me the activity. So I believe I am going to do 4.8 times 10 to the 23, 4.8 times 10 to the 23 divided by 90 equals, I got 5.3 times 10 to the 21. I bet that is mega far off. So I got 5.3. What do we reckon? What's the answer? Hey, check it out now, blood. All right, let's go. That's good. There we go. It's correct. So yeah, if you use these, nice. And that's the end of the question. Okay, end of the quiz, end of the test. What was it? Test, quiz, question. The end of the whole thing. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.